Okay, so recall that last time we talked about the KdV equation. Looks like this. And we were hoping to show that this can be viewed as an integrable system on our infinite dimensional space of functions of the variable x. And we did show a few things about this equation. We showed that this is actually a Hamiltonian system, which follows from writing this equation in the form, well, observing that this thing here is a complete derivative plus u squared. So as we discussed, well, this delta operator here can be viewed as a Poisson structure on the space of functions of x. This thing here is a complete differential. Therefore, this gives us a Hamiltonian form of the KdV equation. That's one thing that we observed. We also constructed a few things that are preserved by the equation. One was the integral of u dx, and all integrals are integrals over the period because we consider 2 pi periodic functions, so integrals are from 0 to 2 pi. Another was integral of u squared dx. And the third one was the Hamiltonian function, which is integral of u cubed minus 1/2 ux squared. So that this, we saw that all of these are conserved. And finally, we also showed that there is close relation of the KdV to the spectral theory of the Schrödinger operator with potential u, specifically the KdV. As u evolves according to this equation, the spectrum of the Schrödinger operator is preserved, which, at least in theory, it gives us infinitely many first integrals, so the eigenvalues of the Schrödinger operator. There are still a few things that we'd like to do. Well, first of all, we'd like to have more explicit first integrals because these eigenvalues there are impossible to find explicitly. In particular, we'd like to sort of extend these three things into an infinite sequence of first integrals which look in the same way. They're integrals of some differential polynomials of u. Hopefully we can do that. But more importantly, we want our first integrals to Poisson commute with respect to our Poisson structure. And it is true that eigenvalues of the Schrödinger operator commute with respect to this, but it's not so clear so far how to show that. So this is sort of what we'll do today. And the way we'll do it is by using the fact that KdV can actually be written as a Hamiltonian system, not just in this way, but there is also a different Hamiltonian representation of KdV. So, and it can actually be quite easily guessed from what we already know. So here, well, we know that, well, this is a Hamiltonian representation. So here, one of our conserved quantities serves as a Hamiltonian function. So now suppose we can find a different Poisson structure and a different Hamiltonian function so that the corresponding flow is still the KdV equation. Then, of course, that second Hamiltonian, that other Hamiltonian function will also be preserved by the KdV equation, because any Hamiltonian flow preserves its own Hamiltonian function. So it is reasonable to expect that, well, one of these conserved quantities can serve as a Hamiltonian function. And for this one, it's pretty easy to figure out that this cannot work because the differential of this is equal to 1. So you cannot find any reasonable Poisson structure so that it will generate the KdV flow. So we'll try to use this. If we compute the differential of this, that's just 2u. Let's divide by 2. So we want to write KdV equation as ut is equal to some operator that's applied to u. We can do so, and if we can show that that operator is a Poisson structure, then that gives us another Hamiltonian representation of KdV because u is the differential of integral of 1/2 u squared. Well, first guess that we could make here is maybe we take delta cubed, that's the third derivative, plus 6u delta. So if I write this, then clearly that's the KdV equation. The problem with this operator here, that's clearly not a Poisson structure because that's not even skew symmetric. If we look at the first, the delta operator is skew adjoint. So the first term here, it is a skew symmetric operator because from integration by parts formula tells us that this is equal to the negative of integral of u prime v. That means that delta is skew symmetric. If we take delta transpose, that's negative delta. So the first term is skew symmetric. The second term is not skew symmetric because when you take the adjoint of u delta, that's going to be negative delta u. When you take adjoints, products of operators, you need to switch factors. So that's clearly not skew adjoint. That doesn't work. However, it's easy to fix it. Namely, well, we need here a u delta term and a delta u term so that they compensate each other when you take adjoints. And it's easy to figure out that if you want to have a coefficient of 6 in total, then it should be plus 2u delta plus 2 delta u. If you expand this, that's the KdV equation. Because 2u delta, that gives you 2u ux. And then 2 delta u, that's 2 delta applied to u squared. That will give you another 4u ux. Altogether, that's the KdV equation. So we see that, well, we don't know so far if that's indeed a Hamiltonian representation because there is we don't know if that satisfies the Jacobi identity, but we were able to write KdV as some skew symmetric operator applied to the differential of a function. So now the question is whether this is indeed a Poisson structure. And the answer is yes, it is. So to understand why, let's look at this expression. So the first Poisson structure that we have, that was just a delta operator. So that Poisson structure, it was a constant Poisson structure in the sense that this Poisson tensor here, it does not explicitly depend on u. So what is a constant Poisson structure? So suppose we have a vector space with a constant Poisson structure. Well, constant Poisson structure, it's a constant bivector. A bivector is the same as a bilinear form, but on the dual space. So a constant Poisson structure is just the same. If you have a constant Poisson structure on a vector space V, that's the same as a skew symmetric bilinear form on the dual of V. And conversely, well, if we assume everything is finite dimensional, which is not the case here, then there is a one-to-one correspondence. If you have a vector space with a skew symmetric bilinear form on it, the dual of that vector space has a constant Poisson structure defined by that bilinear form. And that's the nature of the Poisson structure we had before. That's the delta thing. Here, that's not quite what we have. The first term, delta cubed, that is of that kind. That's independent of u. But here, there is a dependence on u, and it's linear dependence on u. So this part, it's a bivector that depends linearly on u. So here we are looking at linear Poisson structures. So here we have a linear Poisson structure on a vector space V. Well, a linear Poisson structure, as was explained to us by Oscar, that's the same as a Lie algebra structure on the dual space. Linear Poisson structure, it's a Poisson structure such that if you take Poisson bracket of linear functions, that's another linear function. But linear functions, they're just elements of the dual space, so a linear Poisson structure is nothing else but the Lie bracket on the dual space. So linear Poisson structures on V, they are the same as Lie algebra structures on the dual of V. Finally, well, the thing that we have here, it's not quite constant and it's not quite linear, but it's linear inhomogeneous. It has a linear term and a constant term. So that's the third kind of Poisson structures that we can have, is constant plus linear. So this is the type of bivector we have here. So in these Poisson structures, they can be described in the following way. Well, if we look at the linear part, well, if you have a Poisson bivector, which is constant plus linear, the linear part itself must also be a Poisson bivector, so that defines you a Lie algebra structure on the dual. So we have a Lie algebra structure. The constant part, it defines a bilinear form on the dual. So here we have two objects, a Lie algebra structure and a bilinear form. And for the sum to satisfy the Jacobi identity, these two objects, they should be compatible with each other. This bilinear form, it should satisfy what's called the cocycle identity. The cocycle identity, so if omega is a bilinear form, you plug the Lie bracket of x and y and z. So this thing plus cyclic permutations must be equal to 0. Oh, and then, well, Poisson brackets that are of this form, constant part plus linear part, they are in one-to-one correspondence with pairs. Pair is a Lie algebra and a two cocycle on that Lie algebra. It's a bilinear form that satisfies this identity. So, and using this in our setting to understand why this is actually a Poisson structure, we should look at this expression and recognize in it a certain Lie algebra and a cocycle on that Lie algebra. And basically what the Lie algebra is and what the cocycle is we can read it off from the formula. The formula secretly tells us what they are. So the Lie algebra part, we see it in the 2u delta plus 2 delta u expression. And that up to a scalar factor that corresponds to the following bracket on the space of functions. The bracket of f and g is f prime g minus f g prime. And this bracket, it's actually familiar. Namely, if you think of f and g as vector fields, then this is just the usual bracket of vector fields. That's if you compute the usual bracket of f d by dx and g d by dx, that's what you get. So this is this Lie algebra here, because we are dealing with 2 pi periodic functions. This is simply the Lie algebra of vector fields on a circle. And well, that thing does satisfy the Jacobi identity that we know very well, that the usual commutator of vector fields satisfies it.
Translation of a linear Poisson structure.
It's a particular, well, so it's a two cocycle, which is, well, it's called a cocycle for a reason, that it's a cocycle in certain cohomology. The one that you are suggesting, that's a two cocycle, that's a co-boundary. So it's a trivial thing in that cohomology.
You won't do this. Yeah?
So here, the one that we have here is not of that type. It's non-trivial. Okay, so the Lie algebra summand we recognize here as Lie algebra of vector fields, so that part works. And then we need to look at the constant term, and that corresponds to a bilinear form. And again, well, that's the third derivative. So just like this thing, delta, corresponded to the bilinear form, which is integral of fg prime. This corresponds to the bilinear form, which is integral of fg third derivative dx. And that is indeed a co-cycle on this Lie algebra. That's a straightforward calculation to check that this identity is verified. So you need to substitute for f a bracket of two things, two cyclic permutations, see that that's equal to 0. So this is a co-cycle on the Lie algebra of vector fields. It's known as Gelfand-Fuchs co-cycle. And as a matter of fact, so here it sort of pops out automatically, but one can also study a purely algebraic problem, take this Lie algebra and classify all co-cycles on this Lie algebra, and then it turns out that, well, that's pretty much the only thing you can have. There are no other non-trivial co-cycles in some sense on that algebra. So it's a very natural thing. It's pretty much the only thing that we could add to that linear term to actually have a Poisson bracket. So altogether, this shows us that, well, modulo that calculation that we didn't do, that what we found is indeed another Hamiltonian representation for the KdV equation. Very often, you would see people interpret this in a slightly different way. Namely, what you can do, you can add one additional dimension to your Lie algebra and call coordinate in that dimension, call it C, and then put C in front of delta cubed, and then you would sort of make this, turn this inhomogeneous thing into a homogeneous thing just by introducing a single additional parameter. And what that would correspond to a one-dimensional extension of your Lie algebra. That's what's called a central extension, because you get a new Lie algebra which has a one-dimensional center. If you quotient by that center, you recover your initial algebra. And that one-dimensional central extension, well, that basically, the way that works is that that's an extension that's constructed from this algebra using this Gelfand-Fuchs co-cycle, because it's the only non-trivial co-cycle. You get the pretty much only non-trivial central extension of this Lie algebra, and that is what is known as Virasoro algebra. So another way to interpret that bracket that we found is that, well, it's the natural bracket on the dual of the Virasoro algebra, and we see that KdV is, well, it's Hamiltonian with respect to this Poisson structure with this cubic function serving as a Hamiltonian, but it also has a quadratic Hamiltonian, which is the integral of the u squared. The corresponding Poisson structure is the one that lives on the dual of the Virasoro algebra. And so now what we'll do, we'll use this observation to create an infinite sequence of first integrals for the KdV equation. And this time, these first integrals, they will automatically be Poisson commuting. So that will come for free. And one additional observation here that is due to Franco-Magri, I believe, is that, well, we did find here two Poisson structures, but as a matter of fact, there are not just two, but there are infinitely many, and the way you can create them is by combining these two, by taking linear combinations of these two. So you can take this one, and you can add to that a multiple of delta plus lambda delta. Delta is the one that we had before, and that will again be a Poisson structure, and the reason for that is very simple. So adding lambda delta here is basically equivalent to translating u by a constant. That's the same as adding lambda to u. So this when you add lambda delta, that's the same as translating your potential u, and because the two bivectors, they are related, so it's a pullback by translation. So if one of them was a Poisson structure, the other one is also a Poisson structure because they are related through a simple diffeomorphism. So here we are in the situation of what's called compatible Poisson structures. And we will discuss this general setting now and see how such compatible Poisson structures give rise to commuting first integrals. So Poisson structures, so suppose you have two Poisson structures, pi and pi prime, on some manifold M. So you say that pi and pi prime are compatible. So in general, if you have two Poisson structures, you take the linear combination that's not a Poisson structure. This is because the Jacobi identity, it's a nonlinear identity, it's quadratic. So two things satisfy, the sum does not have to satisfy. But here, well, we require that all linear combinations are also Poisson structures. In that case, you say that two Poisson structures are compatible. In fact, because the Jacobi identity is quadratic, it's sufficient that one linear combination satisfies the Jacobi identity, then everything else, all other. So for instance, you could require that the sum satisfies it, then everything satisfies. And that's exactly what we have in our situation. And
Like a Schouten bracket.
yes, that's right. You can explain it using the Schouten bracket, or you could just say because the Jacobi identity is quadratic, Poisson structures, they form a quadratic surface in the space of all bivectors. And if a line meets a quadratic surface at 3 points, then it must lie on that surface. But that's the same thing, yes. Yes. What we also say that a Hamiltonian vector field is a vector field that's Hamiltonian. Well, that can be written as pi dh for some Poisson structure pi and Hamiltonian h. And sometimes it might happen that you can write a vector field in a Hamiltonian way in two different manners, like we can do for a KdV equation. And in that case, that's called a bi-Hamiltonian system, because you can write it in a Hamiltonian way in two different forms. So what's nice about this bi-Hamiltonian systems is that they automatically have a lot of first integrals. And the way you construct these first integrals is as follows. So take a linear combination of your two Poisson structures. Without loss of generality, one coefficient we can rescale to 1. So let's take pi plus lambda pi prime. And well, this thing is because our equation is Hamiltonian with respect to both of them, it preserves pi and it also preserves pi prime. So it will also preserve this linear combination of them. And in particular, well, so recall that for Poisson structures, we often have functions that are called Casimir functions. So these are functions such that the Poisson bracket with anything is equal to 0. And then the claim is, so suppose we have the situation with two compatible Poisson brackets. And let's consider pi plus lambda pi prime, and suppose that each of them has a Casimir function, and let's call that f lambda. So f lambda is a Casimir function of a specific linear combination of pi and pi prime, namely pi plus lambda pi prime. Then the claim is that if you take f lambda and then you take f mu, then their Poisson brackets are all equal to 0. And by Poisson bracket here, you can take any of these Poisson brackets. You can take pi, you can take pi prime, or you can take any of their linear combinations. The reason for that is simple. You take, for this bracket, you take pi plus lambda pi prime, then the first argument is a Casimir, therefore it must be 0. If you take pi plus mu pi prime, then the second argument is a Casimir, so it must be 0. So by linearity, it follows that any Poisson bracket of these two things is 0. Because, well, that's a linear family, and we found two members of the family that vanish on these two things, so all must vanish. And in this argument, one uses that lambda and mu are different from each other, but then by continuity, one can also show that the same thing actually works even if lambda and mu are the same. If you take Casimir functions of one bracket in this family, then they will also Poisson commute with respect to everything else under some assumptions. And the proof is that you just take the limit, mu goes to lambda, so it was 0 in the limit, it remains. So, and here for free, we get a lot of Poisson commuting functions. So we consider this pi plus lambda pi prime. For every lambda, we take a Casimir. So this basically gives us one parametric family of functions, infinitely many functions. They all Poisson commute. Moreover, if we have a system that can be written in a Hamiltonian form with respect to both, then it will preserve all these Casimir functions. So we kind of get, so such a system automatically has infinitely many conserved quantities. Of course, they do not have to be independent because this argument can be made on a finite dimensional manifold there. We couldn't have infinitely many independent functions. So there is no claim here that it produces how many functions it produces, but clearly it does produce a lot. So if we are lucky, then we may get sufficiently many to get complete integrability. And this idea we will now use to generate first integrals for the KdV equation. So for that, we will well, technically, the way I just described it, for that, we need to find Casimir functions for that Poisson bracket that comes from the Virasoro-Lie algebra. That can be done, but it's also not going to be very explicit. And we want to get some functions that look like integral of u dx, integral of u squared dx. To do that, what we'll do, instead of considering these functions f lambda, we'll take f lambda and we'll expand that in power series in lambda. Namely, well, let's consider pi minus lambda pi prime. And in the case of KdV, pi is going to be the delta operator, and pi prime is going to be delta cubed plus and so on. So before we were using pi plus lambda pi prime, but it doesn't matter. It's just a change of parameter. So I want to take a Casimir function of this and expand that in a power series of lambda. And because it's a Casimir function, another way to define a Casimir function is a function whose differential is in the kernel of the Poisson tensor. So we can write that this thing times the differential of the corresponding Casimir function is 0, and I'm expanding that in power series. So I write df naught plus lambda df1 plus lambda squared df2 plus and so on. That's equal to 0. And altogether, if I sum this power series, then I get that Casimir function. And that one is hard to find. However, we'll be able to find, recursively, we'll be able to find these functions dfi. And for that, well, here just do multiplication. And by writing down the coefficients of every power of lambda, we see that there is a relation here, pi dfi is equal to pi prime df I plus 1. So this gives us a recursive way to find these coefficients of the power series for the Casimir function. And this, we'll see, this gives us a method to get infinitely many first integrals for the KdV equation, because it's basically a recursive formula. We'll start with 1, and we'll generate infinitely many. That is known as a Leonard-Magri scheme or Leonard-Magri recursion. So let's see how it works. So we will use this formula to generate infinitely many first integrals. And by the way, these are automatically Poisson commuting first integrals, because as we just discussed, well, these things for different lambda, they Poisson commute with each other, which is equivalent to saying that all coefficients of the power series are also commute with each other. So that's going to be automatic. So let's start with F naught. So F naught.
Science prof.
I, D, yeah, like that, right? Thank you. So let's start with with F naught. So what is F naught? If you plug in lambda equal to 0, and we'll see that pi dF naught is equal to 0. So F naught is the Casimir of pi, and pi is the delta operator. So the Casimir of the delta operator is the integral of u dx. Because indeed, the integral of u dx, the differential of that is 1. That's a constant, and 1 is annihilated by the delta operator. And that's the only thing that's annihilated by the delta operator. So up to a constant factor, pi has a unique Casimir function. That's the integral of u dx. That's gonna be the seed for this recursion. Starting with F naught, we will generate everything else. Let's look at the formula. The formula tells us that pi prime dF naught is equal to pi dF1. So pi prime is d cubed plus 2u, so delta cubed plus 2u delta plus 2 delta u. So applying that to the differential of F naught, which is 1, should be equal to delta applied to d F1. So now here we are applying this operator to 1. This term gives us 0 because that's the third derivative of 1. That gives us 0. This gives us 2 delta u. So it's 2 ux. So the left-hand side here is 2 ux. And that should be equal to delta of df1. So clearly up to a constant, df1 is 2u. Therefore, f1 is the integral of u squared dx. So which is something we already know. We recover the second integral for the KdV equation. And then we continue in the same fashion. So now the new function that we found, we put its differential here. So it's 2u, or we can just put u because rescaling does not matter. And from there, we find df2. Actually, f2 we also already know because we know that the left-hand side is precisely what gives us the KdV equation. And we know also that that can be written, well, and here we have this delta Poisson structure. So that should be the differential of the Hamiltonian of the KdV equation. So the function f2 up to a constant factor, that's u cubed plus or minus 1/2 ux squared. So this recursion, at this point, it just gives us the fact that KdV can be written as a Hamiltonian system in 2 different ways. But the point is that this can be continued, this can be done as many times as we want, and we generate a whole sequence of first integrals, and which can be computed recursively, and this functions automatically a Poisson commute. There is, each time we calculate this, so we plug in something here, and then we, well, that should be the complete derivative of something, and that something gives us the new conserved quantity. And the fact that that's indeed the complete derivative just follows from the way how that was obtained, because that's an expansion of a Casimir in a power series. So if that, assuming that that Casimir exists, that scheme should work. So recursively, we get infinitely many Poisson commuting first integrals for the KdV equation. And
very simple when pi is symplectic, yeah, so you can inverse.
That's right. So if pi, I say, yes, if pi was symplectic, we could write dfi plus 1 is pi inverse times this. So here one cannot invert, so each time we can find the next term up to a constant, because we have delta of something is equal to something. So it's not quite unique, but that is because, well, that Casimir here is also not unique. We can replace it with any function of that Casimir. Therefore, this sequence here.
I think this was the first idea of Magri, when the one was symplectic structure and the other was Poisson, which was...
In the very first paper of Magri on this is actually, he considers KdV, so in that case,
okay.
it's not. So initially, in that paper, I think he doesn't realize that it comes from expanding the Casimir in a power series. So he just uses this recursion to find this sequence of first integrals. But then there is a question of why the recursion actually works, why the thing you obtain on each step is a complete derivative of something, and that follows from this Casimir expansion. So, and this basically shows us that in some sense KdV is an integrable system. It's not quite clear what that means, because recall that integrability on a symplectic manifold means that the number of independent first integrals is 1/2 of the dimension. Here the dimension is infinity, so we did find infinitely many first integrals, which is 1/2 of infinity, sort of, but of course, Arnold-Liouville theorem does not apply automatically in infinite dimension. One needs to sort of explicitly show that the joint level sets of these first integrals are infinite dimensional tori, and the dynamics on them is linear, as we saw happens in the finite dimensional case, and this requires some non-trivial analysis, so it's not for free in this setting. And the last thing that I wanted to briefly mention is the connection of this to what we discussed in the previous lecture. Namely, we saw that the spectrum of the Schrödinger operator is preserved. So which means that we do get infinitely many conserved quantities from the Schrödinger operator. These are the eigenvalues. And now we get an infinite sequence of conserved quantities from this. So we get this sequence of functions fi. So the question is, what is the connection between this? And the connection is basically as follows. So if we look, instead of looking at these functions fi individually, if we look at this power series here, then the claim is that this power series, this basically encodes the information about the spectrum of the Schrödinger operator. This follows from the structural theory of the Virasoro algebra and the connection of that algebra to the Schrödinger operator. So, and specifically, one gets the following thing. So consider this operator. So this operator, it's a second degree differential operator, so it has a two-dimensional kernel. Also, this operator, it has periodic coefficients because U is 2 pi periodic. So what one can do, one can take this two-dimensional space of solutions, shift by the period, and that gives an operator on the space of solutions. So it's basically, if you choose a basis, it's a 2 by 2 matrix that tells you, well, how solutions behave when you shift by a period. In particular, it tells you whether this equation here has a periodic solution or if it's a non-periodic solution. And that 2 by 2 matrix, or an operator on a two-dimensional vector space, that's called the monodromy of the Schrödinger operator. So the monodromy is something you get because if you have a differential equation with periodic coefficients, solutions in general are not periodic. So, and the way solutions behave when you shift by a period, that's encoded by the monodromy. And then, instead of considering monodromy for this equation, one can set that to be equal to lambda f. So we are basically looking at the spectral problem for the Schrödinger operator. And for every value of lambda, one can calculate this monodromy m lambda. So, and this is, it's just sort of another way to think about the eigenvalues of the Schrödinger operator. Because if you know m lambda, then in particular, you know the eigenvalues. So it's kind of the same thing. And then m lambda, it has a property because you have a second order differential equation with no first order term. Using the Wronskian of this differential equation, one can show that m lambda, it always has determinant equal to 1. So up to conjugation, sort of the only non-trivial thing that you have here is the trace of m lambda. And that's a function of lambda that encodes the spectral theory of the Schrödinger operator. In particular, lambda is an eigenvalue if and only if the trace of m lambda is equal to 2. You have a function of lambda where that function is equal to 2, that gives you the spectrum. And then the claim is that if you look at this series here, then up to, again, some scalar factors that you put in front of this fi's, this here is the same as the logarithm of the trace of m. So the generating, we found, the good thing about this fi's that we found is that they're all very explicit. These are integrals of some differential polynomials. But if you do this generating function, that actually knows about the spectrum of the Schrödinger operator. Specifically, it's the logarithm of the trace of this monodromy matrix. And which means that what we did today is sort of the same as what we did last time. The first integrals we found are not really new, but they are functions of the eigenvalues of the Schrödinger operator and the other way around. But, well, now we sort of have a better form of representing these first integrals because they're explicit. And we also see that they indeed Poisson commute. So we do get this complete integrability type behavior for. And I think I'll just